Hello everyone. Today I am going to explain about the Laplace equations, harmonic and conjugate harmonic functions. These two topics from complex functions differentiation. So first we have to discuss about the harmonic functions and Laplace equations. So if you take any analytic function f of z that is equal to u plus iv, if u and v are satisfying the equations del square u equal to 0 and del square v equal to 0, we called as u and v satisfies the Laplace equations. That is, if f of z is equal to u of x comma y plus iv of x comma y is analytic in a domain D, then u and v satisfy Laplace equations del square u equal to dou square u by dou x square plus dou square u by dou y square is equal to 0, and del square v is equal to dou square v by dou x square plus dou square v by dou y square is equal to 0 respectively in D, and have continuous second order partial derivatives. Means that in the analytic function, real and imaginary parts satisfies the del square u equal to 0 and del square v equal to 0, then that 2 satisfies the Laplace equations. Next, definition for harmonic function. If you take any function phi of xy satisfies the equation dou square phi by dou x square plus dou square phi by dou y square is equal to 0, phi of xyz is called harmonic function. So here, solution of Laplace equations having continuous second order partial derivatives are called harmonic functions. Thus, the functions satisfying the Laplace equation dou square phi by dou x square plus dou square phi by dou y square is equal to 0, that function is known as harmonic function. Next, conjugate harmonic function. The function f of z is equal to u plus iv is analytic, and if u and v satisfies Laplace equations, then u and v are called conjugate harmonic functions. Means that if you take f of z is equal to u plus iv is analytic function, and u v satisfies the Laplace equations, then we called as u and v are harmonic functions, and if u satisfies the Laplace equation, v also satisfies the Laplace equation, u is a conjugate of v or v is the conjugate of u. So these two are called harmonic and conjugate harmonic functions. Next, going to the small proof on harmonic functions, show that the real and imaginary parts of an analytic function are harmonic. So, real and imaginary parts of analytic function means u and v. U and v satisfies the harmonic functions. We have to check it by using f of z is equal to u plus iv. So, first you have to write let f of z is equal to u plus iv be an analytic function. By CR equations, dou u by dou x is equal to dou v by dou y, that is equation number 1, and dou u by dou y equal to minus dou v by dou x. First we have to write the f of z and take the CR equations. After that we proceed with CR equations. That is, the first CR equation is dou u by dou x, that is equal to dou v by dou y. Differentiate partially with respect to x, we get equation 1, that is dou square u by dou x square equal to dou square v by dou x dou y, because of we are differentiate with respect to x to dou v by dou y, so that's why we get dou square v by dou x dou y, that is equation number 3. And again you have to go to second equation differentiate partially with respect to y, we get dou square u by dou y square, that is equal to minus, already negative sign is there, minus dou square v by dou y dou x. So if you add these two equations, means from equation 3 plus equation 4, we get LHS, we are adding both dou square u by dou x square plus dou square u by dou y square equal to dou square v by dou x dou y minus dou square v by dou y dou x. So that value is 0 because of v is having continuous partial derivatives. So that's why second order. So that's why both are equal. In general, both are not equal. So here v is having continuous partial derivatives of second order. So that's why we are equating these two, and that value is 0. So next, going to U satisfies Laplace equation, so U is harmonic. And again equation 1 differentiate partially with respect to y, we get dou square u by dou y dou x equal to dou square v by dou y square. And equation 2 differentiate partially with respect to x, we get dou square u by dou x dou y equal to minus dou square v by dou x square. This will write as dou square v by dou x square is equal to minus dou square u by dou x dou y. We are add 5 equation 5 plus equation 6, or here negative sign is there, we can use subtraction also. 5 minus 6 means equation 5 minus equation 6, we get dou square v by dou x square minus of minus plus dou square v by dou y square is equal to, we have to write dou square u by dou y dou x minus dou square u by dou x dou y, that value is 0. V is also satisfies the Laplace equation. V is also harmonic. Thus U and V are harmonic. Hence the theorem is proved. So means that if f of z is analytic, U and V are harmonic functions. Next, going to a small example on harmonic functions. If f of z is equal to e power z, then show that u and v are harmonic functions. First, you have to take the u and v, means that from f of z we have to separate the real and imaginary parts. That is, f of z is equal to e power z, that is equal to e power x into cos y plus I sin y, because of e power x plus iy. Write as e power x into e power iy. E power iy is equal to cos y plus I sin y. So that's why we can get e power x into cos y plus I sin y. So here u real part equal to e power x cos y, and imaginary part v is equal to e power x sin y. So e power x cos y, first order derivative with respect to x, dou u by dou x, symbolic form ux is equal to e power x derivative is e power x and cos y is constant, and second order derivative for u, that is uxx, dou square u by dou x square symbolic form of is that is uxx. E power x cos y derivative e power x cos y, because of e power x derivative is e power x only, so that's why e power x cos y. Next, dou u by dou y with respect to y, e power x is constant, cos y derivative is minus sin y. Next, dou square u by dou y square, that is u y equal to minus e power x, sin y derivative is cos y, and going to v is equal to e power x sin y, dou v by dou x equal to e power x sin y, dou v by dou x differentiation, dou square v by dou x square, that is vxx is equal to again e power x derivative is e power x sin y. Next, going to dou v by dou y, vy equal to, with respect to y, e power x is constant, sin y derivative is cos y. Next, dou square v by dou y square equal to, here e power x is constant, cos y derivative is minus sin y. Next, going to the harmonic function, you have to write dou square u by dou x square plus dou square u by dou y square equal to, so dou square u by dou x square, uxx value is e power x cos y, uyy value is minus e power x cos y, value is 0. Next, here vxx value is e power x sin y, vyy value is minus e power x sin y, so value is also 0. So that's why if f of z is equal to e power z, u and v satisfies the Laplace equations, means that u and v are called harmonic functions. So next problem is, show that u equal to e power minus x of x sin y minus y cos y is harmonic. So here the given function is in terms of x and y. If you find the partial derivative with respect to x, at that time y is constant. If you find the partial derivative with respect to y, at that time x is constant. Carefully you can find here. So first you have to write the given function u, differentiate equation 1 partially with respect to x and y. So first we have to differentiate with respect to x, so that is dou u by dou x equal to e power minus x means that we have to use uv dash plus vu dash formula. So that's why u is e power minus x. So x sin y derivative is sin y, x derivative is 1 into sin y. So minus y cos y derivative is 0. So that's why we get sin y only, sin y minus. Why we write minus in the formula, plus is there, but we are writing minus means here e power minus x derivative is minus e power minus x. So plus into minus is minus, minus e power minus x, and we can write v as usual, x sin y minus y cos y. Then going to the second order partial derivative, dou square u by dou x square. So e power minus x derivative is minus e power minus x into sin y is constant, minus again we have to use u v dash plus v u dash formula, that is minus e power minus x, x sin y derivative is sin y, x derivative is 1 into sin y plus y cos y derivative 0 plus e power minus x into, because of here e power minus x derivative is minus e power minus x, minus of minus plus, plus e power minus x into x sin y minus y cos y. You can simplify it, we can get the e power minus x sin y, e power minus x sin y, both are negative, so that's why we get minus 2 e power minus x sin y plus x e power minus x sin y minus y e power minus x cos y. This is dou square u by dou x square. Next going to dou u by dou y. Here x terms are constants, so that's why we can find the derivative for only y terms. E power minus x is constant, keep outside, and x sin y derivative, x is constant, sin y derivative is cos y, plus y cos y derivative by using the formula u v dash plus v u dash, that is we can write as cos y derivative is minus sin y, so that's why minus of minus plus y sin y. Next we can write plus into minus, minus y derivative is 1 into cos y, so that's why minus cos y. And next going to the second order derivative, dou square u by dou y square equal to e power minus x into, here x is a constant, cos y derivative is minus sin y plus, so y sin y u v dash plus v u dash, you can use it, y derivative is 1 into sin y plus y into sin y derivative is cos y plus here cos y derivative is minus sin y, that's why minus into minus plus sin y. So you can simplify it, we can get here sin y plus sin y, 2 sin y, so that's why here minus x e power minus x sin y plus 2 e power minus x sin y plus y e power minus x cos y. After that add equation 2 and 3, we get dou square u by dou x square plus dou square u by dou y square equal to 0, because of, if you go to the RHS part, here plus x e power minus x sin y, here minus x e power minus x sin y, both are cancelled, and minus 2 e power minus x sin y, here plus 2 e power minus x sin y, both are cancelled, and going to last term minus y e power minus x cos y, here it is plus, so that's why all the terms are cancelled in RHS part, so that's why it is equal to 0. U is harmonic. Next example is, so this is one of the proof based on the harmonic function, that is, if f of z is equal to u plus iv is a regular function. Regular function means analytic function of f of z in a domain D. You have to prove that del square modulus of f of z whole square is equal to 4 into modulus of f dash of z whole square. So here del square means dou square u by dou x square, means dou square by dou x square plus dou square by dou y square of modulus of f of z whole square, means that here u is equal to modulus of f of z whole square. So that's why first we have to proceed with f of z. So f of z is equal to u plus iv, we know that, and here f of z is analytic, so that's why it should satisfy the CR equations, that is dou u by dou x equal to dou v by dou y, ux equal to vy dy, and dou v by dou x is equal to minus dou u by dou y, or dou u by dou y is equal to minus dou v by dou x. You can write any way. So that is Vx is equal to minus uy. Going to modulus of f of z means modulus of u plus iv. So that is the length of f of z. We can write, by mistake here it is minus, it's a plus. So then modulus of f of z is equal to under root of u square plus v square. So then modulus of f of z whole square is equal to u square plus v square. Because of here the length of f of z means under root of u square, real part whole square plus imaginary part whole square. So that's why we can write here under root of u square plus v square. Then whole square, if you apply square and root is cancelled, then we can get the u square plus v square for modulus of f of z whole square. Now we can go to the del square of modulus of f of z whole square, that is dou square by dou x square plus dou square by dou z square of modulus of f of z whole square. So modulus of f of z whole square value is u square plus v square. You can substitute it. Dou square by dou x square of u square plus v square plus dou square by dou y square of u square plus v square. So that is dou square by dou x square u square plus dou square by dou x square v square plus dou square by dou y square of u square plus dou square by dou y square of v square. We can find it separately and substitute it. Going to next one, dou by dou x of u square. First order derivative we have to find it, and we can write dou by dou x of u square equal to, so first derivative, u square derivative is 2u into u derivative is dou u by dou x. Going to the second order, dou square u by dou x square of u square, here we have to apply uv, that is uv dash plus vu dash formula. 2 is constant right outside, and u into dou u by dou x derivative is dou square u by dou x square plus dou u by dou x into u derivative is dou u by dou x. So that's why we can write dou u by dou x whole square. Next, going to dou square by dou y square of u square. So we can write dou by dou y of 2u dou u by dou y, that is equal to 2 into, again we are applying uv, so uv dash u into dou square u by dou y square plus we can write dou u by dou y into dou u derivative is dou u by dou y. So that's why dou u by dou y whole square. So now going to dou square by dou x square of u square plus dou square by dou y square of u square equal to, we have to substitute the values, 2 into u dou square u by dou x square plus dou u by dou x whole square plus 2 into u dou square u by dou y square plus dou u by dou y whole square. So here we can write 2 common, and we are adding the terms dou square u by dou x whole square plus dou u by dou y whole square plus u into u common from these two terms, u into dou square u by dou y square plus dou square u by dou x square. So if u is a harmonic function, then this equation equal to 0. So that's why we can get here 2 into ux whole square plus vx whole square. So means that we can write here dou u by dou x whole square. Why we write vx here? We know that dou u by dou y is equal to minus dou v by dou x from CR equations. So that's why we can write here minus dou v by dou x whole square value is dou v by dou x whole square, because of negative sign is cancelled, because of it is a whole square term. So that's why we can write here vx whole square. This value is modulus of f dash of z whole square. square. So that is how to write it is equal to modulus of f of z whole square. We know that f of z is equal to u plus iv, and derivative of f of z is dou u by dou x plus I dou v by dou x, ux plus I bx. So modulus of f dash of z is equal to under root of ux whole square plus uy whole square, but here we can write as vx whole square, and here also it is a vx whole square. Vx whole square, we can write it as vx whole square. So why here it is a, you can write dou u by dou y also vx is equal to, but we can use the vx because of by using CR equations dou u by dou y is equal to minus dou v by dou x. So that's why it is equal to ux whole square plus vx whole square for f dash of z. So that value we are substituting here. So this is the proof to find the del square mod f of z is equal to, we have to prove it is a 2 into modulus of f dash of z whole square. That's all for today.